In this talk, I'm going to discuss how to improve detection sensitivity by estimating hemodynamic response shape instead of adopting canonical HRF. Let me start with some data unrelated to fMRI. We have 66 data points for speed of light. As you can see by the histogram, most of the data points are clustered, but there are two outliers. How do we estimate the speed of light with those 66 data points? Well, we learned in basic statistics, we can use one sample t-test. So as you can see at the bottom of the right-hand side, that's the result from one sample t-test. The result, we get the point estimate plus the uncertainty range. But definitely we would be worried about the impact of those two outliers. Can we do something better? Some people may argue that the non-parametric approach would be a better alternative. So that's the green result. So in this case, the point estimate, I believe, is much better, but the problem is the uncertainty range is pretty wide. Can we do something different? Yes. Then we can, of course, we can throw away those two outliers. So that's the result of the blue result. You can see that's the third from the bottom. So in this case, you can see the uncertainty is much improved. But the problem with this approach is that removing outliers is a little bit arbitrary. Where to decide the cutoff? So that's the last approach, is we don't make the traditional Gaussian distribution. Instead, we assume that those 66 data points follow student T distribution. So with this approach, then you can see the result is roughly similar to the outlier removal approach, but we get rid of the arbitrariness associated with outlier removal. So there are two lessons we can learn from this example. First, we don't adopt the typical decision-making approach based on T statistic or P value. We don't have to make a reject or accept the null hypothesis. Instead, our focus is about how to achieve accurate estimation and get the precision of the estimation. So that's our focus. The second thing we can learn from this example is we can learn from the data. We have some prior knowledge. So we learn from the data, but we don't fully trust the data. So that's the combination of the two. We can achieve some satisfactory result about the speed of light estimation. So let's keep those two lessons in mind. So how can we improve detection sensitivity for fMRI data analysis? So everybody is familiar with the canonical HRF, right? So the shape is totally fixed, the total duration is fixed, the peak, where the peak occurs is fixed at 5 seconds. The duration of the overshoot and the duration of the undershoot are fixed. And the depth of the undershoot is also fixed. It's about 9% of the peak height. So we know there's a huge amount of variability across different brain regions, across different individuals, across tasks, across different groups, right? So for example, in this case, this is an estimated HRF from insula. As you can see, the total duration, the undershoot duration, and the undershoot duration is dramatically different from the canonical HRF. Also, there's an initial dip right after the stimulus onset, and the peak occurs around 3.5 seconds, a little bit earlier than the canonical curve too, right? More importantly, the undershoot is about the same depth as the peak height. So there's a reason we can improve the canonical curve approach. So we can make comparisons between the two approaches. With canonical HRF, the cost is low. We only need one fixed curve, one regressor. In contrast, if we want to estimate the hemodynamic response, we'll have to use many regressors to capture the shape subtleties, those features, right? So that's the cost is high. But in terms of like risk and the gain, well, we know there's pretty high, reasonable, moderately high extent of risk, we may lose some detection sensitivity. So hopefully, if we're willing to pay the high cost, we would be able to gain some accuracy, precision, and sensitivity. That's our goal. So how can we do that? Well, across all the major software packages, we already know at the individual level, that approach is already available, right? So there are different names. People call it TANS, sticks, or finite impulse response, right? So basically, we put in multiple sticks or TANS across some duration. Then we measure the hemodynamic response at those time points. In the end, we get something at the right-hand side. We have those sampled data for the hemodynamic response. So this approach is available. Why are people not using this approach? Well, the challenge is not at the individual level, it's at the population level. The complication is that since we have many sampled time points for the hemodynamic response, how do we say something about the presence or absence of the hemodynamic response, right? If we have two HRFs, how do we compare them? That's the challenge at the population level. So that's the thing we want to try to solve. So suppose at the left-hand side, we have those 14 data points that captures the hemodynamic response shape with some number of individuals. How do we assess that? The presence or the compare different HRFs? Well, in this case, instead of using linear splines, we use nonlinear splines, more specifically smooth splines. Here I'm showing 6 different splines, starting from the simple one, the horizontal curve, the black one that captures the baseline. Then there's a linear spline, which is the dashed red line. You can see from the lower corner to the upper right corner. So that's the diagonal line that captures the linearity. Then we can go further up, then we can see the increased nonlinearity, the complexity of the nonlinearity. So we have more basis functions. We have more splines, we capture a higher degree of nonlinearity. So with those that set of smooth splines, we can capture a smooth hemodynamic response curve like the right-hand side, the blue curve. So that's our workflow of estimate hemodynamic response functions at the population level. So this approach has been implemented in FNA with the program 3D MSS. So this approach is data-driven, but also we don't fully trust the data. We have leveraged some regularization processing involved. So let's apply this approach to a whale data set. So in this data set, it's a 2x2 design. So for each individual participant, we have 2 conditions. The first condition is congruent. It's a tension experiment. The congruent condition, as you can see at the first column on the left-hand side, is a big letter is composed with the small letter. It's the same small letters as the big letter. So for example, H is composed with little h's. So that's congruent condition. The incongruent condition, the second column on the left-hand side, is the big letter is composed with small letters, but those small letters is different from the big letter. So the big letter H, you can see, is composed with the small letters of S. So those are the 2 conditions. Then we have 2 groups of individuals. We have 44 healthy volunteers and 43 bipolar disorders. So those are 2x2 design. Then there are other parameters. The TR is 1.25 seconds. They're shorter than usual. There are about 300 trials per condition. So those are the experimental parameters. At the individual level, so we adopted 2 approaches. First, the conventional canonical HRF, right? So each condition, we use the one regressor fixed shape to estimate the hemodynamic response. So we have 2 conditions, we end up with 2 beta values per individual. So the second approach, we're going to estimate the hemodynamic response with 14 basis functions. They're linear, in this case, the TANS, linear splines. So each condition will end up with 14 sampled data points. That's individual level. Then when we go to population level, So again, corresponding to each of the two approaches at the individual. Now each individual have two betas per per individual, right? So two beta values. Then we have two groups. So at the population level, we run 2 by 2. That's ANOVA. How about the estimating the hemodynamic response approach? In that case, remember each condition will have 14 sample data points. So we're going to use the smooth splines. So that we use the program 3D MS to assess compare groups, compare conditions and the interactions. So first of all, let's look at the overall, the omnibus effects, right? So the first row is the conventional canonical HRF results. Second row is the smooth HRF, the estimation approach. 3 columns. First column is the main effective group, right? That's basically compared to groups. Second column is the main effective task condition. So we compare congruent versus incongruent. Third column is the interaction between group and the condition. So overall, you can see that the second row is much more sensitive, right? So the smooth HRF approach is way much more sensitive than canonical HRF. So that's the big picture. But let's zoom in to take a closer look at the two scenarios. The one scenario, we focus on this two group compare the incongruent condition, right? So on the left, the first column on the left-hand side, you can see of course, the overall, the group comparison under this incongruent condition, the smooth HRF approach is way much more sensitive, right? But if we look at this focal point, the crosshair, we can look at the comparative two approaches more specifically, this particular voxel in insula. So you can see the canonical HRF will have the two betas, right? The red one versus the blue one. You can see they're slightly different, but you can see the two error bars are overlap with each other. So the traditional studies will see, well, there's some slight difference, but they will not reach some threshold, right? So we are not confident to say they're different. But look at the bottom row. So there are two different HRFs. Instead of compare two scalar to numbers, now we're comparing two one-dimensional curves. So now you can see the two curves is much more different than just comparing two numbers. So in this case, the sensitivity is much improved, right? Now let's look at the second scenario. In this case, we're looking at one group, healthy group, under the congruent condition. This is just one condition for one group. You can see the for the canonical HRF, you can see most of the brain regions have some evidence showing the presence of a hemodynamic response, but not all of them. But nevertheless, even the white matter, you can see the green crosshair shows at that focal point, even the white matter shows some evidence for the presence of a hemodynamic response. But if we look at the smooth HRF approach, pretty much the whole brain has some evidence showing the engagement of the hemodynamic response, right? So again, in this case, we're using the whole HRF, the one-dimensional curve, to assess the evidence for the presence of hemodynamic response, instead of just using one number, which is the scaling factor of the fixed hemodynamic response. So this shows also something that has been in the literature. People talk about the whole brain involvement, including white matter, but this is a better approach, I think, more sensitive approach to show the presence of hemodynamic response, even in white matter. This slide shows that the cross-individual differences in terms of hemodynamic response. This is still in insula, in this particular region. I'm showing extract 12 individuals. You can see their shape, even under both conditions, congruent and incongruent, they have pretty much similar, the overall shape across conditions and across individuals. However, there are two major differences across individuals. The peak height, right? So that indicates the extent of hemodynamic response magnitude is different across individuals. But another tricky thing is the undershoot. The relative magnitude of undershoot, how deep the undershoot is quite different across individuals. That's something quite different. We still don't fully understand the mechanism for undershoot, right? So it's that's about recovery, that's just how much we see, but the real mechanism is pretty complicated. So in this case, most of the time we focus on the overshoot, the peak, but that's not necessarily the case for undershoot. There is some subtlety about the magnitude of undershoot. That's something in the future, maybe it's interesting to further explore the situation. So that's inter-individual variability. This is a cross-region variability. So here we show 5 different hemodynamic response features. So the first one is the overall peak magnitude. You can say, of course, globally across different brain regions, the magnitude is different. Well, that's understandable. But the second row shows the depth of the undershoot. So they also vary quite substantially across brain regions. The third row shows the ratio of peak versus the depth of the undershoot. So that also varies, right? So this is the log, the scale is the log of the ratio. The fourth row is the duration of the overshoot. So that's time to peak, basically shows. So there's some extent of variability. The last row shows from the stimulus onset to the nadir of the undershoot. So they also varies. As far, you can see those 5 hemodynamic response shape features, there are quite a substantial amount of variability. So there's no wonder the canonical HRF would have trouble to adapt, to globally across different regions. So to summarize, so I hope I have demonstrated that the hemodynamic response, there are some varying extent of variability. I think the biggest variability is across different brain regions. Across groups, across task conditions, across individuals, they are more subtle, not as large as across different brain regions. So in terms of modern approach, I hope I have convinced you that the estimation approach is a better way to go. So it improves accuracy, precision, and detection sensitivity, right? So that's, I believe that this estimation approach is much can improve the canonical HRF with some small of cost. We either pay estimate with more aggressors, or we have to work harder. And the modern approach, of course, it's not familiar to most people, right? So in addition to the improved sensitivity, another benefit is that we can visually see the estimated hemodynamic response. So we see those curves, we can immediately recognize the signature shape, right? So to have the overshoot, the undershoot, and maybe sometimes you will have an initial dip. That shape, we know that. So we can use that shape information to convince ourselves. That is purely based on statistical value or p-values, right? So also, this is also aligned with our philosophy of modeling. We focus on not a decision making, whether you have the hemodynamic response or don't, or whether you have difference or you don't. No, we focus on estimate. Of course, there's always uncertainty that is associated with the precision or standard error, for example. So the approach is now publicly available in FNE. There's a program called the 3D MMSSS. There's a blog. Then this approach has been just published recently. So in your image.